transform now. It says these are expressions. No, they're not, of the functions. Okay, let's go. So actually what this example shows is that you can't really just tell by looking whether it's going to be a difficult job for you or not. Like these two look fairly similar, but the first one's very easy and the second one is not. So you're looking at the first one, it's not in the tables, so you should do a partial fraction expansion. You need to factorize the bottom. So seems to think that this can be done quite quickly. Let's see, s squared plus 4s plus 3. As usual, I will use the AC method. So that's 1 by 3 giving me 3. What are the factors that adds a prime? So it's just 1 and 3. Does that make up 4? Yes, it does, which means it will factorize. So you have s squared, and then the 4s, we'll use that 1s. We'll rewrite it as 1s plus 3s plus 3. Equal to, take out s out of the first term and you're left with s plus 1, and then take something out of that again that leaves s plus 1. So what you could take out is 3 times s plus 1, and now you've got a common factor of s plus 1, so you take that out and you're left with s plus 3. So this actually becomes quite an easy one, because once you factorize big F of s, factorize the bottom that is, you have two rule ones, and if there's two rule ones you can just do the cover up method. Okay, so we have big F of s, which is equal to 6s over, now I won't write s squared plus 4s plus 3, I'll write s plus 1 times s plus 3. We can simply do the cover up method. So the theory gives us two rule ones, constant over s plus 1 plus constant over s plus 3. I'll write them just for a moment and then get rid of them. So constant, constant, and that we can do this. So the cover up method gives us these constants kind of very, very quickly. So the kind of write it the way I was doing. So for s plus 1, what you have to do is cover up s plus 1 and see everything that's left. 6s over s plus 3. And what you do is you put a value of s into that. That makes the bottom, the s plus 1, equal to 0, and that would be minus 1. Job done. Now unfortunately I can't undo that, I think, without messing it up. So this is messing around a bit too much. But we can do it. Okay, so now for s plus 3, you cover up s plus 3. See what's left. 6s over s plus, it says 11, but that should be plus 1. Okay, and what makes s plus 3 equal to 0? The answer is minus 3. So you put minus 3 into whatever is left. And hopefully that means we can tidy it up quite easily. So the first one is minus 6 over 2, which is minus 6 over 2 is minus 3. Drawing a funny blank there. Minus 3 over s plus 1. And the other one is minus 18 over minus 2, which is plus 9. And now we can send this back linearly, term by term, fixing the constant. So that's big F of s. So it goes back to little f of t. So fixing the minus 3, the 1 over s plus 1 goes back to e to the minus 1t. Fixing the 9, and the 1 over s plus 3 goes back to e to the minus 3t. And this one, if when we're looking at differential equations, there's two different exponentials, so that means it's overdamped. Okay, so the first one is relatively easy. Now I know you probably haven't done examples yet, but you will be quite soon. Okay, now let's look at the other one. So similar story, we'll try and factorize the bottom of big G. So we do what we've got, s squared plus 4s plus 13. AC is 1 by 13, which is 13. But that's a prime, so the only factors are 1 in itself. And you can't make up 4 with that, so that didn't work. So what you need to try now is factorizing it using the minus b formula. So you get s equal to minus b minus 4 plus or minus square root of b squared, which is 4 squared minus 4ac. And what's happened, 16 minus 52 is square root of minus 36. The thing inside the square root is negative. So you have here no real roots, and that implies no real factors. So that's a disaster for you. You can't factorize it anymore. So all we're going to say now is, okay, what we look in the tables again, and all it looks like is maybe s over s squared plus omega squared, or maybe omega over s squared plus omega squared, but with the s shifted. So that's all we can really say here. So what we're going to do is we're going to write the bottom, we're going to complete the square at the bottom, and that'll send us on our way. So s squared plus 4s plus 13. We want to write this as s squared plus omega squared, except with the s shifted to s plus a. So we want to be able to do this. So how do we do it? We multiply out the right hand side carefully, and we get s squared plus 2as plus a squared plus omega squared. And we compare both of these. The s squared and the s squared, that's good. Now let's compare the s's. I have 4 s's here. I have 2 s's here, so those numbers must be equal. And let's look at the constants. So I have 13 here and a squared plus omega squared here. So we're talking 2a is equal to 4. Okay, divide both sides by 2, I get a is equal to 2. And then come over the other side, we have a squared plus omega squared is equal to 13. That's the purple bit. A is equal to 2, so that's 4 plus omega squared is equal to 13. Take away the 4 from both sides, omega squared is equal to 9. And then we can do the square root of both sides and get omega is equal to the square root of 9. Now, strictly speaking, as an algebra problem, 2 solutions, plus or minus, but we can just pick one of them. You can run with minus 3 if you want, if you're a bit daft. You can do that. So we have, what have we got? We've shown that s squared plus 4s plus 13 is equal to s plus a, which is s plus 2 squared, plus omega squared is 3 squared. So let's write out our yoke again. What's on top? 4s plus 8. This yoke is called big G. So g of s is equal to 4s plus 8. Is that what it was? 4s plus 8, yeah. Divided by the s squared plus 4s plus 13, but we completed the square on that to get s plus 2 squared plus 3 squared. Now this is not so easy. I think what we said last time is if you break it up into 4s over that thing and 8 over that thing, it's a bit messy. It's easier just to take out the common factor of 4 initially. And if you take out the 4 initially, you're left with s plus 2 on top, because 4 by s is 4s and 4 by 2 is 8. And we have this. And now this is actually exactly a shifted 4 cos 3t. Let me just make it a bit more explicit. Jeez, Friday, I better put the Guinness in the fridge. Okay, so now we're comparing this with the 4. We can just sit there for the moment. And what's in the tables? We have s over s squared plus omega squared. Excuse me. Just thinking about the Guinness, I shouldn't have been. S squared plus omega squared. And then the s's are shifted to something. So that's kind of what we're looking at. So this thing that we have, the big G of s, is 4 times, it's exactly a cos 3t, but it's shifted. So when we send it back to little g of t, to account for the shifting, the plus t2, we multiply it by what we call exponential shift e to the minus 2t. So we have therefore little g of t equal to, so shifting's first shift theorem says send it back as normal, 4 cos 3t, then multiply it by the exponential shift e to the minus 2t. And that's that. I don't have any picture here or anything like that.